is Dhagash Mehta, a senior manager of investment strategies, machine learning, and asset allocation at the Vanguard Group based in the greater Philadelphia, Pennsylvania area in the US, where he has been building a research group in machine learning and finance in general. He's been applying machine learning in financial portfolio construction methodologies for measuring risk aversion and other psychological attributes, liquidity prediction, investors' behavior research, ESG analytics, etc. Dhagash completed his part 3 of mathematical tripos at the University of Cambridge and pursued his PhD between the University of Adelaide and Imperial College London in theoretical particle physics. He then pursued his postdoc studies at various institutes such as the National University of Ireland, Syracuse University, University of Cambridge, Simons Institute of Theory of Computation in Berkeley, and the Fields Institute in Toronto. He was a research professor of applied and computational mathematics at North Carolina State University and then at Notre Dame before moving to industrial research. Prior to joining Vanguard, he was senior research scientist at Raytheon Technologies Research Center working on machine learning and optimization for aerospace systems. Dhagash is on the editorial advisory board at the Journal for Financial Data Science, has organized numerous conferences on applied mathematics, machine learning, and finance, including a NeurIPS workshop in 2020, and has guest edited journals on machine learning and mathematics. And today he's going to be speaking to us about mutual funds similarity using graph machine learning.
Thanks very much, David, for a nice introduction and also inviting me here. Thanks a lot to your whole team. I've attended a few talks and I'm enjoying them, and I hope I can also go through some of the recordings for the talks I've missed so far. So I'm currently at the Vanguard Group, which is a large mutual funds company. I'm working on this project on my own. So this is my personal research interest. Of course, everything is my personal research interest. But to make sure that I do this, give this disclaimer, these views are just my own, not my company's. Don't get me in trouble. This work was done in collaboration with 2 extremely bright young machine learning scientists, Dhruv Desai and Vipul Satone. The paper is already out on arXiv. This is the link on your screen, and it's also submitted to a conference. So these are fairly preliminary results, and that's why we went to a conference. We are still refining these results, and we are making it even more mature work, and hopefully eventually we'll go to a journal paper. We came up with this cute name, Fund to VEC, because we are applying Node to VEC, which is a very popular graph machine learning technique, to mutual funds domain, hence Fund to VEC. Okay, so that might already give you some hints on what's coming next. But let me start by defining the whole problem, and I'll spend some time in clarifying what I'm after eventually, what is the bigger picture here, and so on. This is a 1-hour talk, so I can present everything in more elaborate fashion, and it's also a technical audience. Please feel free to stop me anytime and ask me questions. So let's start. What I'm after, the bigger picture in my mind, is some sort of product similarity tool. And this is the question that I'm after. Given a product, what are other similar products? The second question, which is basically a rephrasing of the first question, is how similar are 2 given products? If you are given 2 products, can you quantify the similarity between them, or maybe the differences? Product similarity is also known as peer analysis, competitors analysis, and so on in the financial world. People have been working on this kind of problems in different names. It's one of the most frequently arising problems in most business areas, not just finance. For example, in Amazon recommendation system, if you start searching for some particular product, it will then start recommending you a similar product. How do they define similarity? That's a whole interesting game here. Similarly, Netflix movie recommendations, if you watch one particular movie, it will start recommending you other similar movies. So that's also product similarity. In our world, in my case, the product is a mutual fund or an ETF. I'm going to use this fund or mutual funds, which will also include ETFs for the purpose of this talk. That I'm not making any distinction between them. So mutual funds already includes ETFs. So that's my problem. Product similarity, or more specifically, mutual fund similarity. Why would I be interested in this? Many different applications that I've seen in the financial services in general, not just quantitative finance, not just investment management, but in general financial industry. And just to list out a few of them, one may be sales and marketing, where the if your sales guy goes to an investor and he sees that this end investor has some of your competitors' products or competitors' mutual funds, to be more specific, can this salesperson then can run this mutual fund similarity tool. Let's say a hypothetical tool that you already have. Run it, identify the most similar fund to the one that your end investor has in their portfolio, and which is homegrown, and then then the salesperson can start pitching your homegrown product to this end investor, saying that there are some other advantages such as better brand name, low expense ratio, and so on. So that's an immediate application. Sales and marketing, that's exactly what Amazon or Netflix would do. The second one would be alternative portfolio construction. Let's say you have a fund of funds, a portfolio constructed only of funds. They all are from your competitors' funds. Can you start replacing each of these funds by your own homegrown fund while still retaining the overall risk return profile? Product similarity tool or fund similarity tool can be extremely useful there. Portfolio diversification. Sometimes you may have 10 funds in your portfolio, but it turns out that many of these funds are just similar to each other. And in turn, you are not as diversified as you think you are. So that's where you want to run this similarity tool to identify portfolio diversification. Or you can come up with some good measure of portfolio diversification based on this mutual fund similarity tool. Similar funds with different theme. If you want to invest in a particular theme, for example, say ESG, which is very popular these days, then, and if you already have one mutual fund which is not an ESG fund, then you can try to run this product similarity tool, find the most similar fund to the one that you already have, but now has ESG theme in it. And then you can replace your existing fund with a similar but ESG fund. Competitors analysis. Mutual fund managers would always like to keep a track on their competitors' funds or their peers. And for peer analysis, this mutual fund similarity tool can be extremely useful as well. Tax loss harvesting. In many countries, especially in the US, sometimes it is better to realize loss by selling a mutual fund which is underperforming or which is making loss at the end of the year. Hence, you can gain in tax. And then immediately buy a similar fund so that you still have the same risk return profile. So it has very nice name, tax loss harvesting. And you can also use this kind of product similarity tool to do this. Sometimes you may find that a particular mutual fund is performing really well or becoming very popular in the market, and it's your competitor's fund. You run this product similarity tool to identify the most similar fund to that popular fund. And then you find that there is no homegrown mutual fund, which is really similar to the one that is very popular. It means that you have identified the gap in your homegrown mutual funds portfolio. And you might want to launch a new fund based on this analysis. So launching new products is also one of the applications. There are maybe many other applications. And you can, here I'm describing everything with regards to mutual funds similarity, but you can also use more or less the same arguments to come up with, say, stock similarity tool, bond similarity tool, maybe private equity fund similarity tool, and so on. So I'll just focus on mutual fund similarity. There are indeed many applications for such a mutual fund similarity tool, or in general, mutual fund similarity computation. People have thought about this problem in the financial industry. And there are some options that people go to traditionally. The most popular approach is this first one, the third-party categorization, such as Morningstar categories or Lipper categories. So it is essentially a lookup table, and it is updated every month, because every month you have new data from mutual funds, from SEC, for example, and each mutual fund is assigned a particular category. And then when you are trying to identify a similar fund to the fund that you are investigating, using this one of the categorization methodology, what you are supposed to do is you identify the Morningstar category for this particular fund that you are investigating, go to the lookup table, find all the funds that are in the same category, and those funds will be similar funds to the one that you are investigating by definition. So that's very easy methodology, just a lookup table, and extremely popular. It's, however, partly relying on qualitative approach, in the sense that they do have data, the expert committees in the categorization panels, but they might also have their own input, their own human biases, and so on. More importantly, because this process involves some human in the loop, they might be slightly biased, or at least they are black box up to a certain extent. And most importantly, there is no ranking. So I know that all these 100 funds which are in the same category are similar to the one that I'm investigating. But then which fund is more similar? Which of these 100 funds is more similar than the other 100 funds to the fund that I'm investigating? So there is no ranking here. The second approach is compute overlap between two portfolios using, say, Jacquard index or weighted Jacquard index, and so on. It does capture the bigger picture, but granular details may be missing sometimes. Compute Euclidean distance between each pair of mutual funds in the chosen variable space. And then it's also very valid and quantitative way of measuring similarity, but it might not capture nonlinearity because you are assuming that it's a Euclidean distance, whereas the actual manifold underlying the data might be highly nonlinear. Compute cosine similarity, which is probably a better way compared to Euclidean distance, but it might also not capture nonlinearity completely. Many other unsupervised methods which do capture nonlinearity, but sometimes they don't scale and so on. Okay. Here is what we came up with. So first, we do not want to use aggregate level information for each mutual fund. We do not want to use only how much percentage of this mutual fund is invested in retail sector, tech sector, maybe country, and so on. We want to come up with a more objective computation of similarity. And at the most basic level, in the sense that we want to compute the similarity of mutual funds based on their underlying assets, underlying holding data, not aggregate level data. So here is the starting point for our framework. So let's say for each snapshot in time, you have tabular data for mutual funds and their holdings. So here in the US, at least in SEC websites already have publicly available information every month. So they update mutual fund holdings every month. And you can just scrape it for free. It's publicly available information. So this is how the tabular information would look like each month. Let's say you have some n number of mutual funds. Then the number of rows is equal to the number of mutual funds, fund 1, fund 2, fund 3, and so on. On the columns, you have asset 1, asset 2, asset 3, and so on. Say Amazon, Google, Facebook, Apple, and so on. The entries in this matrix is nothing but the portfolio weight of this particular asset in this particular fund. So point 2 here means that mutual fund 1 has asset 1, and asset 1 is essentially 20% of mutual fund 1, and so on. So this is a rectangular tabular data. For the purpose of this presentation and this work, we restrict ourselves to only index equity funds, mainly due to easy data availability reasons. There are some 1,093 or so funds in our data. Total assets were 16,000 or so. So this is a rectangular table. In our case, 1,000 or 1,100 or so rows and 16,000 columns. Okay. So this is just raw data, but then we started putting them in a specific pictorial representation. So for each fund, I'm putting a red circle or red node, more technically, and I'm putting them on the left-hand side. So fund 1, fund 2, fund 3, and so on. They are my individual nodes. Similarly, for each asset, I'm also putting a node. Now, blue node, just to distinguish them from fund node. Again, there are 16,000 assets, so there are 16,000 nodes here. Then I put a link between them. If this particular asset, asset 1, is in mutual fund 1. If some asset is not in a particular fund, then I do not put a link between them. For example, so asset 3 is not in fund 2, so there is no link between them. And that is how I create a whole network from this tabular data. It's exactly the same tabular data. I have not changed anything. It's just a pictorial representation of the same data. Okay, underlying data is the same. No approximation going on. But In addition, I also have some more information in the table. I also know the portfolio weight of each asset. And hence I put weight on each link as well. For example, asset one, if you remember in my tall fake example, asset one was 20% of mutual fund one. And hence I put 0.2 in this on the link, and so on. So all the links now also have weights. In short, from this tabular data, I have just created a pictorial representation, and it looks like a network. And more specifically, it is a bipartite network. Because each fund is only connected to an asset node. There cannot be any link between two funds. A fund cannot be in another fund, at least in this particular data. I know that there are, of course, some target date funds which are fund of funds, and there this network will not be completely bipartite. But here in my simpler data set, I have very clean bipartite network where there is no fund which is in another fund. Similarly, a stock cannot be in another stock. Amazon stock cannot be in Apple stock, for example. And again, it's just simplistic data that I have. Of course, there might be some special cases, but I'm ignoring them right now. I do not have them in my data. So this is in general. So this is specifically weighted bipartite network. It's bipartite and then also weighted. Okay. So bipartite weighted networks, they arise in many different areas in science and engineering. So for example, various social networks are weighted bipartite networks. Movie actors network, that's also a bipartite network, not necessarily weighted though. Protein-protein interaction, that's also bipartite weighted network, genome network, and so on. Even flavor ingredient networks. So Barabasi and his colleagues have been working on flavor ingredient networks. It's also clean bipartite network. People have been studying these networks for a while now. Although less technical quantities worked out for bipartite networks and less so for weighted bipartite network compared to regular networks. So that was one of the challenges that I faced. To just give you some, to show you some pretty picture from our data. So this is how our actual bipartite, weighted bipartite network looks like for this 1100 funds and 16,000 assets. And this is one way of representing this bipartite network. It's called concentric circular representation. So in the inner circle, we have all the funds as our nodes. In the outer circle, all the nodes are assets, and every now and then they are connected with each other. So that's as a pictorial representation, doesn't help us in any way. It's just for the presentation purpose. For if you are interested in probably less dense picture, I also plotted this for say 7 or 8 funds, and these are my asset nodes in the outer circle. So this is also a nice visualization. Again, doesn't help much. Okay, so I presented this the same tabular data in terms of bipartite, weighted bipartite network. But eventually, I was interested in mutual fund similarity, right? Where does the similarity go? So now I have to talk about similarity on the network. There are many different options to define similarity on a network. The most basic one might be node degree similarity. So for example, if two nodes on a network have the same number of nearest neighbors, then these two nodes are similar. In this example, node 1 and node 2 have the same number of nearest neighbors. They are more similar than node 1 and node 3 because node 3 has 5 neighbors as opposed to 4 for node 1. So that's a basic definition of similarity. You can also be more complicated. For example, not just nearest neighbors, but how about next to nearest neighbors? And in this case, node 1 is similar to node 3 because it has the same structure, not just at nearest neighbor level, but also next to nearest neighbor, as opposed to node 2. Even more complex definition, clustering coefficient. Clustering coefficient is easily defined in terms of real world scenarios. So let's say you have 10 friends and we are interested in computing your clustering coefficient. Then the clustering coefficient just means how many of your friends are also friends of each other. You might have 10 friends, and meaning that there may be 10 choose to possible number of connections among your friends. But then sometimes your friends are not friends of each other. It's just you who is the one who is connecting them. And hence your friendship network might be, or network of your friends might be sparse. So this fraction is essentially the clustering coefficient. How many of your friends are friends of each other? And if your definition of similarity is clustering coefficient, if two nodes have the same clustering coefficient, then they are similar. Then in this example, for example, node 1 will be more similar to node 2 compared to node 3 because they have the same clustering coefficient. By the way, I cannot see the chat right now. If you have any question, please feel free to, or maybe David, please feel free to stop me and ask.
We do have a question in the chat.
Please go ahead.
Alan, if you want to ask the question, please go ahead.
Okay, good afternoon. I was wondering, how do you keep track of these fund similarities when the funds rebalance their portfolios? Do you just create a whole new graph when there's a major rebalancing beyond funds, or do you have any way to keep track of the funds who were similar and now are not so similar anymore? How does this work?
So far, I'm just focusing on one particular snapshot of time. So I have data only from one snapshot. So it's static right now. But dynamic similarity is even more interesting. And I'm not there yet.
Okay, thank you very much.
I think that's extremely interesting and important. You might have to imagine a dynamic network. So each month the network just changes, and you have to keep track on this similarity, keep track on what fund went to which cluster and so on. But I'm not there yet. I'm just focusing on one particular snapshot right now.
Okay, thank you very much.
Can I ask a question?
Sure.
On this page, there are lines connecting two blue nodes. So what does that mean when there's connected?
So this is just an example, very basic example. I wanted to show how clustering coefficient is defined. In this case, you can imagine that this node is connected to some another node.
Yes, I understand the line between the red and the blue, which means the fund is contains.
Very good. So I understand the confusion.
Yeah.
The confusion maybe because of so original network is bipartite network. And then red dot is only connected to another blue node. But here I'm just coming up with some toy example.
Okay. So in the toy model, what does it mean when two blue nodes are connected? What does this line stand for?
Here you can think of some friendship network.
Like two securities are similar to each other?
Or maybe one security is, yeah, you can think of that. Or maybe they are correlated with each other.
Okay, all right, thank you.
And there is also, I should point out that clustering coefficient and many other quantities are more rigorously defined for regular network. For bipartite network, you have to come up with your own definition. There is some work in defining clustering coefficient, for example, for bipartite network, but it becomes extremely complicated. In this presentation, I just wanted to show the basic definition of clustering coefficient, and hence I assumed a small regular network. So, and this confusion, actually, I should point out that this confusion is valid, and there are some technical reasons behind this confusion. I had to choose this kind of examples. I could not use a completely bipartite network example. So moving on, so say here, there is also another notion of similarity on network. It's called homophily. So if two nodes are in the same community, then they are more similar to each other than two nodes which are in different communities. So in this case, and by a community on a network, I mean click. So a completely connected subgraph, or maybe at least partially connected subgraph. So this is on the screen. A part of this network is creating a small subcommunity, and node 1 is in that community. Node 2 is also in the same community, and hence node 1 and node 2 are more similar compared to node 1 and node 3. So there are all these kind of notion of similarity on a network. If I was doing traditional machine learning or traditional statistics, I had to come up with all these different ways of defining similarity. So basically, I had to create all the handcrafted features myself for each node, and then I had to compute some cosine similarity or some other computation to the final similarity. However, we are in the modern days with modern machine learning techniques at hand. So my strategy was to let a machine learning algorithm itself define or identify all these important features and come up with a good definition of similarity by itself. So I don't want to do all this handcrafting of features. I'll let algorithm decide on which nonlinear relationship would be more important for my purpose. Okay? So that's why I went for this novel graph machine learning algorithm called Node2Vec. And here, what it does is it learns the features from the raw data. It does representation learning, which is what deep learning or modern day machine learning is famous for. I'll, of course, it's a very technical topic, Node2Vec itself. I don't want to go into too much detail. I would rather go to the next step, the metrics stuff quickly. But here, just briefly, so Node2Vec is based on Word2Vec. You might have heard of Word2Vec. It's a word embedding using deep network, or rather shallow network. So let's assume that you have a good Word2Vec implementation. What Word2Vec does is it identifies semantically similar words. There, you are supposed to feed sentences, and then Word2Vec will identify semantic similarity based on your input data, which are sentences. The sentences are nothing but directed graphs. So in a sentence, starting from the first word, you can imagine an arrow going from the first word to the second word to the third word, and so on. And eventually you have a directed subnetwork or subgraph. Each sentence is basically directed subgraph. You feed it in this Word2Vec, and then it will identify semantic similarity among these words, among the nodes of these many different subgraphs. So let's say you have this Word2Vec. The problem with Word2Vec is that it only accepts this kind of specific structure as input, namely this directed subgraphs or sentence-like structure. I want to use Word2Vec for my network, but my network is ordinary network. It doesn't have any directions. It has weights, but there is no directions. There is no sentence-like structure. So here is the trick that this Aditya Grover and Lesovic came up with from Stanford, and they called it Node2Vec. You still want to use Word2Vec for normal graph, but and hence from the normal regular graph, you create sentence-like structure. And how do you create these sentence-like structures? Starting from each node, you do a random walk, say of length L, say 10, length 10, meaning that from each node, you start hopping from one node to another and stop at the 10th node. And it's a random walk, so you are basically going to a randomly chosen path. This whole path becomes a sentence because now it has a similar structure as a sentence. You go from the first node, which is your starting word, and then you go to the next word in a directed fashion, and then the next word, next node, and so on. You have created a sentence of 10 words. And you do this multiple times, starting from the same node, so that you have many sentences starting from the same word, so to say. And you do this for all the nodes. So in the end, you create a fake or a new database which looks like sentences. And then you feed it in Word2Vec. It's very nice, elegant idea. You'd think, why didn't I think of it? And it's that kind of simple idea, but works really well in practice. Once you generate this fake database, you put it in Word2Vec, and then it will come up with semantically similar words or similar nodes in network terminology. There are some hyperparameters to tune in, and then to make sure that the training is done well and you are trying to optimize the metric that you have chosen, and so on. So eventually, you can use node2vec for any type of network, and you can still come up with node similarity, same as word2vec. Okay. So that's a node2vec in a nutshell. And then it will give you a lower dimensional representation, lower dimensional embedded representation of the data, where the similar nodes will be placed together in this new representation. That's the whole point of word2vec as well. So that's good. We can use this node2vec for our data. But then what metric should we use to evaluate the goodness of our embedding? How can we claim that our embedding, our new representation or new similarity is good? Or even better, can we claim that it is better than some other notion of similarity? So the first part, coming up with this network representation of the data and using node2vec, was easy. We finished it very quickly as soon as we got the data. 1 whole year was spent then to come up with a good metric. And then we realized many other things on what's going on in the literature of these embeddings. How can we claim, even in the NLP world, that one particular word embedding, say word2vec, is better than another, say, I don't know, glow or BERT? How can we claim that one word embedding is better than another? Is there any objective metric? And that's what made us very confused, especially in the literature. That people are using so many different ways to claim that the one embedding is better than the other, and so on. But we found that most of those were not objective metric. Many times what people would do is that they would have some downstream task. So after word embedding, if the downstream task, for example, summarization, is doing good in one embedding versus another, then based on that result, they would claim that the embedding is better. But it's based on the downstream task, not the actual embedding. Sometimes they might also have a list of similar words which are universally accepted, agreed upon. Can one embedding reproduce all this similarity, or all the words in the list of list that is universally accepted, as opposed to the other embedding? If one particular embedding is reproducing all the similarity of words from this list accurately as opposed to another, they would call it better embedding than the other one. However, this is just one particular list out of so many millions of words. So again, it's very narrow definition of goodness or better. That's what we kept realizing. How can we claim that our embedding is better than another representation of the same data? And then here is probably a more philosophical distinction between supervised versus unsupervised learning that we realized. Usually the definition of supervised versus unsupervised learning goes like, if you have a target variable, then the learning is supposed to be supervised. If you do not have a target variable, then you are doing unsupervised learning. Here is my unrefined definition at the moment. If you have a priori metric to evaluate an algorithm for your task, then it is a supervised learning. If you do not have an a priori metric to evaluate your algorithm, then it is unsupervised learning. A priori is to be more emphasized here. If you already had a metric to evaluate your clustering algorithm, for example, then you could have just created one more column based on this a priori metric, which would be then your target metric, in theory, of course. And then it would have been a supervised problem. It was never a unsupervised problem. The distinction here is that you do not have an a priori metric for unsupervised learning. That's a whole interesting game here in the unsupervised world. And I am now in the finance department, not in applied math departments, as I used to be at Notre Dame and many other schools. And I learned many interesting things. It's a very scholarly, deep area, finance, economics. They have been thinking about many of these things that applied mathematicians also think about. And I came to know about this law called Goodhart's law. The more refined version of this Goodhart law says that when a measure becomes a target, it ceases to be a good measure. And that's very striking, a very enlightening statement. That applies really well to unsupervised domain. So, okay, enough about philosophy. What can we do here in our node to vec problem and our font similarity problem? So once we learn this embedded representation, we had to come up with our own domain-specific metrics to evaluate the embeddings. And I think that was the most interesting part here. So, but what can we do in the beginning? So at the most basic level, here is what we know about our data. Our data is bipartite network. That's the ground truth. That's for sure. That means that we have two distinct set of nodes, fund and asset. The embedded representation, as learned by node to vec, should at least be able to distinguish these two types of nodes in the representation that it learned. That's a basic most thing it has to do. Can the embedded representation distinguish fund and nodes? So how can we do that? So once we learn an embedded representation at some specific hyperparameter point, we then do k-means clustering in this embedded representation. Does this k-means clustering distinguish fund data points and asset data points in separate clusters? If not, it might not be a good embedding. Move on to another hyperparameter. So that's what we did. And on the in the left, you are seeing a table. So each hyperparameter point, we are computing k-means, and then the optimal k, where the k is number of clusters. And then our metric here would be v measure, how well we reproduce or how well we cluster font nodes or font data points and asset data points in this embedded representation space. So that's what we did. And then we found that this particular hyperparameter point 16, 128, 128.1, at that point, the k-means was clustering them most cleanly. And that's how we came up with our good embedding. This is our best embedding from node to vec. It's still not 100%, but it can still at least cluster them, roughly speaking, 86% of the times. This particular embedding is what we call fond-to-vec. This is the best embedding from our data and from our computation. Maybe there are some other hyperparameters which might still be better, but with our available computer resources and how many hyperparameter points we could go through, this is the best we could come up with. So this is what we call fond-to-vec. If you are curious, at this particular hyperparameter point, on the left, upper left corner, you are seeing the t-SNE plot. So this is how well it clustered all the fond and asset nodes. There were 5 clusters, not 2 clusters. That's exactly why we used V measure and not homogeneity and no other completeness and so on. We used this V measure. So that's the, and these are the clusters. So this is basically funds and assets in each cluster. If a cluster is made of funds, it's mostly funds, and or assets, it's 99% of asset, and so on. Okay, so they are fairly clean clusters. So that's why we think that this is as good as we can come up with all the limitations we had. The second metric was, so we are thinking, can we come up with some sort of similar words as they do in NLP world? Can we, do we have some nodes which are definitely similar? So here we have this S&P 500. So there are some funds which are index funds and they track S&P 500. They have to be similar up to tracking error. We also chose another index, Russell 2000, and they are also funds which track Russell 2000 are also similar, supposed to be very similar, except that there are 2000 assets there, so that it's more likely to have larger tracking error, and sometimes fund managers don't have access to all the 2000 stocks. They work with only a few, maybe 1000 funds and so on. So there is more mismatch there. So these are the funds tracking a particular index such as S&P 500 is our list of thesaurus. So thesaurus, similar words. Can we reproduce these as similar words in the embedded representation? So these are our results. And we are doing mean cosine similarity. So for example, there were 27 funds which were tracking S&P 500 in our data. Mean cosine similarity among these 27 choose 2 pairs within fond-to-vec. So in the embedded representation was 0.99. So they were indeed placed very close to each other. As opposed to in the original data, we did mean cosine similarity and it was 0.97. Slightly better, not significant. Russell 2000 was more interesting. In the embedded representation, mean cosine similarity was 0.95, whereas in the original space, it was really low. And it might be because of some less number of assets usually in such large index. And we are still trying to identify the reasons behind this. We are doing some explainability here, but these are our preliminary results. So at least words that have to be similar, so to say, are similar in our embedded representation. So that's another metric that we came up with. So there we also created a few other metrics to evaluate the goodness of our embedding, to be very explicit, our punchline of this work is not that font2vec is better than the original representation of the data or any other representation of the data, because it is a genuinely unsurprised problem. We do not know a priori what we mean by similar fonts. We do not have any ground truth definition. And hence, it's a genuinely unsurprised problem. How can you compare two mutual funds objectively? Maybe an extreme example, how can you compare between, say, Mars chocolate and Hershey's chocolate? Of course, you can start with percentage of cocoa and many other things, but then there are also some subjective aspects. There is no scientific definition of similarity here. In mutual funds world, probably the situation might be better, but still there is no specific definition of similarity here. What I'm claiming is that this font2vec is a different view of similarity of mutual funds. That's the punchline. And the how different, what do I mean by different? I mean that I am trying to identify structural similarity on the graph among this mutual funds data. So that's the that's a whole punchline. And in short, we are doing social network analysis of funds and ETFs. There are many other applications I have in mind, for example, direct indexing. Sometimes you want to replicate an index, but with less number of assets and so on. So that's direct indexing. Anyway, so I'm also running out of time. So this is my conclusion. Product similarity is very interesting area, and we are using different techniques. I strongly encourage you to look into this problem. It's a very interesting problem. I'll stop here. I'll take questions.
Okay, thank you very much. We have a question in the chat from Brian. So if you want to unmute yourself, Brian, you can ask your question.
Hi, great presentation, by the way. So this is just a more of a, I guess, a little bit of more of a deep dive on your V metric that you've chosen here. I'm not sure if you covered specifically how it's actually being computed based on the results after you have determined your k-means. Because in this case, I believe, so in slide 34, I think you have your summary for, so where you have your split of the different clusters, and you separate it into, so for asset cluster, you have your assets and your funds, but then you're determined it based on how much assets or how much funds is in that particular cluster and classify as either asset cluster or fund cluster. But this looks like it's just a raw percentage based on everything that's in that cluster, while if you think about it, the percent of funds that are actually available versus the percent of assets that's actually available is largely different. So there's a pretty heavy skew if you have a lot of assets. For example, if you were to have like maybe 400 funds in one cluster and 9,000 assets in that cluster, well, that cluster has almost all the funds, but then it also has most of the assets. What would you even classify that as? Asset cluster or fund cluster? It's a little bit unclear.
So, so the challenge here was that you have two ground truth labels, asset and fund. But then when you do k-means, ideally k is equal to 2 should give you two distinct clusters, but that's not what we found. We found that sometimes k is equal to 5 was the best cluster, best clustering. And then how do you compute this mismatch or match between the ground truth labels and the clusters? So there are 2-3 ways. So homogeneity and completeness, both combined in V measure, but then V measure would also weigh more on this homogeneity sometimes and so on. But fortunately, there is a parameter beta in V measure, which gives more weight on homogeneity versus completeness. We did trial and error, and beta is equal to 0.01 was making sense. But I agree, it's probably also not very scientific.
Okay, so do you have a justification? Because yeah, I guess you did say that you did some trial and error for choosing your beta, but why is 0.01 a good beta? Like, how is the weight between completeness and homogeneity determined?
So by trial and error, I meant the robustness. So I think 0.01 was giving us the same numbers as opposed to 0.015 and so on. So there was some robustness there. But again, I think you can certainly argue that 0.01 might not be the correct number. And on the other hand, I do not know a good way, maybe another alternative measure, which can give me what I'm looking for. I have 2 ground truth labels, but then the number of clusters I'm getting is more than 2. How can I compute the mismatch? Or how well I have clustered? That was my...
Okay, I understand. So I guess this is more of a follow-up question. So I guess you did say that there is only 2 ground truth labels, but is any part of this process you would work that into the actual data? Because fundamentally, if you are just to look at funds and assets, there may not necessarily only be 2 clusters. There could be different types of assets and different mutual funds, and each one is going to have a different cluster. They might be close to each other, the clusters, compared to the distance between all the funds and mutual funds, obviously, because it's a bipartite graph. But I'm not sure if you can necessarily say that there is fundamentally only 2 clusters just because you have a bipartite graph.
I'm not saying there are fundamentally 2 clusters. I'm saying there are fundamentally 2 labels, fund and asset. So stating it differently, I do not want an embedding which says that this fund is similar to Apple stock.
Okay.
I want to have an embedding which has to give me similar funds when I enter ticker symbol of a fund, and not an asset. So that's why we created this metric.
Okay. So I was a little confused by what the V metric is actually measuring, because it sounded initially like you were just saying that what is the difference between, why is there a difference between 5 different clusters versus 2 different clusters? But this is more like saying, is there any clusters that contains both funds and assets, and sort of penalizing?
Yeah.
Okay. Thank you.
Okay, thanks very much. I think that fills